Welcome back, everyone. This is our first seminar of the semester, 2025. As you probably know, we have these seminars every week where we have people from inside and outside Princeton. And today we're very lucky to have Professor Parastoo Abtahi, who is a faculty member here in the Computer Science Department. I met Parastoo we were just talking about 2019, when she was still at Stanford. And I remember she was finishing her PhD, working on some really inspiring work in the AR, VR space. At the time, I used to work at Snapchat, where we were doing that kind of work, and I was very, very impressed by her work. I remember going back to talking to my colleagues at Snap, being like, we really need to hire this person. She's amazing. Her research is super cool. And then eventually I joined Princeton, and I came back to Princeton. I was like, we need to hire her. Let's go for her. And she was not even on the job market, but we convinced her to interview here at Princeton, and we were very lucky that she accepted our offer. And then I remember when she accepted, she said, I'm going to go do a postdoc for a year. Can I defer to do a postdoc at Meta? And I was like, oh no, she's going to love industry, and it's going to end up not coming back to Princeton. But luckily, she came to Princeton, and she's been here for now 2 years. Yeah.
A year and a half.
Yeah, no, yeah. We taught together a class on Introduction to HCI last year. And so it's been wonderful to have her here. And one of the things that I've been kind of been more and more convinced about is that the kind of research that she does really can inspire a lot of the thinking that we do here at CITP around policy. And I feel like just in general, like the space of spatial computing, in addition to obviously the AI space, is picking up at a fast pace that maybe we're ignoring because paying so much attention to LLMs. And so I hope that her talk today can help us think kind of what the challenges and opportunities around this new technology that I believe is going to be here in a few years, and it's just going to be so pervasive, and it's going to impact a lot of things we do. So with that, Parastoo.
Thank you so much for the introduction, Andres. I'm really excited to be here and talk to some of you. I see some students who've taken my grad seminar in the audience, which is great. I'm very happy to be here. Today I'm going to talk about some of the work I've been doing with my students on perceptual manipulation and spatial computing. So just to give maybe a little bit of context, if you've never heard of the term spatial computing before, I think within HCI we tend not to agree on terminology. There are papers on what is the definition of mixed reality or spatial computing, and the answer is people don't agree on what those terms mean. And I'm going to tell you what I think my definition of spatial computing is. So I think about generations of computing as going from mainframe and personal computers that were stationary, where we invented specific hardware input devices like the mouse and the keyboard to interact with them, to the age of mobile computing, where we had ubiquitous computing, different devices of different sizes that were now portable so we could carry them around with us, and the interactions we had with them were closer to how we interact in the physical world. So we now have some form of touch interactions and pen input, and with the age of spatial computing, we now have computing that is increasingly integrated and spread out in our surrounding spaces, with the smart devices that are interconnected, with the robots that are autonomous moving around in our spaces. And I think one of the enabling technologies here are wearable devices. So devices that you wear, like glasses, VR, virtual reality, or augmented reality headsets, that really take this notion of computing being on a 2D screen to computing now being situated in the physical spaces that we're in.
Can you mute your computer? I hear you coming out.
I think it's muted.
Okay.
I also hear an echo, but it's not me. Maybe.
I don't hear it anymore. I think it's good now.
It's okay? Yeah. Okay. So and the interactions we have with these computers are also getting closer to how we physically interact with people. So we use gaze and gestures and voice commands, and getting closer to really having digital information integrated with the physical space around us. So today I'll be talking about specifically these hardware wearable devices like AR and VR headsets. And I think this is an exciting time to be doing this type of research, because while VR and AR have been around for decades in research contexts, they've recently become commercialized. You may have seen some of these headsets on the news or try them out. We have virtual reality headsets like the Vive, We have MetaQuest 3 Vision Pro. These are headsets that are both virtual reality, that enable both virtual reality contexts, but also augmented reality pass-through. So you can't see through the glasses, but you have cameras that capture your surrounding environment and reconstruct the physical space around you. And then we have these glasses, AR glasses that are see-through AR, that enable digital information to be anchored in physical spaces and be interactive. And we also have glasses that don't have a physical display, but there are still wearable devices that have a camera that capture our surrounding environment, and you can use them to do, for example, audio queries. So I'll start from some of the early work I've done on the left side of the spectrum, and you'll see kind of the shift in terms of the research throughout, going from left to right to more AR interfaces. So I think most people, when they think about VR, they think of entertainment, gaming. So I always like to start off with a few applications where I think VR is good for. And those are applications where there are experiences that you wouldn't have otherwise, you wouldn't have access to. Maybe it's too expensive, or things that are flat out impossible. For example, I can experience what it would be like to be in the International Space Station, and maybe I couldn't have access to, had access to this experience otherwise. I think VR is a great opportunity for learning because it takes advantage of our innate spatial reasoning skills. Here I'm showing an example of people interacting with 3D molecular structures. And also VR is great for this type of training, that it's better to have some sort of training before you kind of transfer that learning to physical spaces like fire safety or surgery and things like that. And these are just examples of VR applications that I find compelling. Of course, there are a lot of other examples. So when you think of these examples, and if you've tried a VR headset before, visually you see a lot of exciting content. The graphics have gotten a lot better, tracking is much better, but in terms of the other sensory experiences that you could have, they're very limited. For example, your sense of touch, the best you can get with these commercial headsets nowadays is a controller like this that you hold in your hand, and it vibrates when you touch something. And so really our sensory integration in terms of haptics and sense of touch is really lacking with these commercial headsets. So this is what I started my PhD thinking about. How can we make haptic devices for these commercial VR applications? When we think about how we interact in the physical space, we touch different surfaces, we feel their texture, we feel the forces of objects, and this force feedback enables us to have these very improvisational interactions with objects, because we know their stiffness, their weight, and also we can have these dexterous manipulation tasks using our hands. But when we put on a VR headset, we see something exciting, virtual, but when we reach out to touch these objects, there's nothing really there for us to feel. And so this is what I started thinking about during my PhD, and I had this idea: what if we had a bunch of miniature drones, basically, that moved around in space and orchestrated this haptic interaction? So this is the time where actually Snap was coming up with these miniature drones, and drones were becoming more affordable and smaller. And I was thinking, what if we had these drones move around in space, and as you wanted to interact with something, we could predict what this object you were interested in interacting with would be. And then these drones would move around in space, and they would find either a 3D printed object or an everyday object that would resemble the physical properties of that virtual object, and they would bring them to you. And you would touch them, and you would feel the force, you would be able to grasp them and manipulate them. And my advisors let me work on this, which now as a professor I find very fascinating. And so I set out to do this, and the application I focused on was, what if maybe you wanted to do e-commerce and you wanted to buy a piece of fabric. You wanted to reach out, feel the texture of the material you were buying, or the weight of the hanger that you were holding. How could we use drones to make this happen? So I implemented this with only one drone first. So this is a custom racing quadcopter that we wrapped in an enclosed mesh. So it's completely enclosed so that you can't touch the propellers. And then we also attached different fabrics, different 3D materials to it, and we integrated into this virtual scene so that as you would move, we would predict what object you would be interested in interacting with. We would send the coordinates to the drone that would autonomously move there so that when you reached, you could feel the objects there. So this is me trying to show this example that I earlier showed. So here I'm feeling the texture, I'm grabbing the hanger, I feel the weight of the material, and we had different fabrics around the drone, so depending on the hanger you were touching, you would feel velvet or silk or other textures. So if you noticed in that video, the drone was not the most precise robotic system that you've ever seen, and this was a huge problem. If you're in VR and you can't actually see the drone, you don't know where it is. So if you reach out and touch something, if it's not exactly where you want it to be in space, you will not feel anything because you don't know where the drone is. So the problem here was that the drone had a limitation, and we needed to address this limitation somehow to make this haptic system work. And this is not unique to this unusual drone system. Any haptic device like a controller, a glove, or even any type of encounter type haptic devices that were traditionally a robotic arm, they have some form of limitations, whether it's the speed, the resolution, or the precision in space. These are limitations of these devices that if we want to build affordable hardware, we need to overcome. So the insight that I drew on during my PhD was that the human perception is limited, and we can leverage this to make these devices appear as if they work better. And to demonstrate this, I'm going to ask everyone, this works much better in person than Zoom calls, to try to touch your index fingers together. You get one shot. I saw a lot of what I consider cheating. but I think what you notice there is that you actually have a very noisy sense of where your finger is in space. And that makes it really difficult to make your two index fingers connect. And that's because your sense of proprioception is limited. And this is exactly what I mean by our human perception is limited, and we can leverage that to our advantage in these interactions. So I'm going to talk about two projects that I worked on during my PhD. The first one is the drone example that I just showed. So in this example, we were able to attach different fabrics. We were able to attach 3D props like hangers. And the drone itself could also act as a box, a passive box that would fly and land on different surfaces. And the problem I just described is that ideally what you would want is as users reach out to touch a virtual object, you would want the drone to be positioned exactly at that contact point. But in reality, what happened was that the drone sometimes would drift and not be positioned perfectly where we needed it to be. And this is partially because we have this enclosed mesh, all these fabrics, these asymmetric, unusual 3D printed objects attached to it, and it made it really difficult to position the drone really precisely. So to address this, what we did was we drew inspiration from this work from 2016 at CHI, where they had one physical cube on the left, and they mapped it to three virtual boxes. So it was kind of a magic trick where visually you would see yourself touching three different virtual cubes. But when you took off your headset, you would only see one physical cube in front of you. And if you try this, it was really neat. It was a really nice magic trick. And we really needed to understand how did that magic trick work so that we could apply it in this context where the user was moving, the object was moving, and so was the drone. And it wasn't this controlled kind of experiment where all components were stationary. So to do this, we started looking into how the brain plans and controls movement. So think about the very simple case of reaching out to touch something. When you reach out to, let's say, grasp an object or touch an object, what happens is that your brain sends command signals, motor command signals to your body. That in turn results in your arm moving forward. And when you move your arm forward, then you need to use your sensory system, your sensory organs, to get some information back in terms of what happened. So you use For example, what you see, where your hand is in space, as well as what you feel, the proprioception, the forces in your arms and muscles, to gauge how far you moved and where your hand is in space. And you use this information to continuously basically update the motor command. So the brain compares where it expected the hand to be with where it actually is based on the sensory information, and then uses the difference to update the sensorimotor command, and continuously does this in order to allow you to do this form of goal-directed reach. So what we did in this project was, as you're reaching out, if the drone drifted to the left, we would drift your arm very slowly in the opposite direction. So your brain starts compensating for this error by shifting your real hand further left. And what happens is that you end up with this mismatch between where your real hand is and where your virtual hand is. And if this discrepancy is small enough, you don't even notice. So as you're reaching, you start shifting your virtual hand in the opposite direction. And so you move your real hand to the other way. And this allowed us to make sure that people could always make contact with the drone, even if it was slightly offset, or even if it was drifting. And if this discrepancy was small enough, they wouldn't even notice that we were doing this. And the reason this works is exactly what I tried to communicate earlier. So now I'm going to ask everyone to do the same task, but in front of you. You get one shot, and you can look at your finger. I think in most cases, everyone is successful in this task, and that's because your sense of vision is not as noisy as your sense of proprioception. And the brain knows this. The brain knows that the sensory signals from proprioception are noisier, and it weighs vision over proprioception. So when there's slight incongruency between the two, it believes what it sees over what it feels in some sense. And this is known as the visual dominance effect. And this is exactly what we're kind of taking advantage of in this interaction. So we had people come into our lab and try this e-commerce application and try different scenarios. And overall, everyone was able to make contact with the fabric, pick up the objects, but we did find some limitations in terms of if they moved really fast, or if they were really close to the object, or if the drone moved in certain patterns or moved too fast. It was really hard for us to apply these sorts of illusions. So this takes me to the next project, where we try to do a more systematic way of studying how far we can take these illusions before people notice them. So shifting gears here a little bit to a different haptic device. So in this project, we used a shape display. How many, who's here familiar with shape displays? Okay. So shape displays are basically matrices of actuated pins. They move up and down. They have been developed primarily out of MIT Media Lab, where they think about this idea of tangible computing. How can we have computers that are not 2D pixels, RGB colors, but actually physical pixels that move? And in this case, we're using shape displays as a form of haptic device in VR. So our goal here is not to have a tangible computing system necessarily, but just a haptic device for VR. And the problem here is that the pins on the shape display are relatively large, meaning that the display is relatively low resolution. And this is because every pin has a motor, and the more you miniaturize these motors, the more expensive the hardware becomes. And so this is a limitation, again, where in order to build affordable haptic hardware, we need to kind of compensate for this low resolution. So here's a video of me trying this pentagon maze on the shape display. And here you see that the pins are relatively large, which means it's really hard for me to follow without getting my finger caught in these uneven surfaces. And so we were trying to address this low resolution with similar types of perceptual illusions. So here the task is not reaching to touch something, but it's more of a contour following task where I'm touching the surface of an object. So the first thing we tried, we called it angle redirection. And here the problem is, how many here have tried Paint before, Microsoft Paint? Okay, this is not too bad. I think increasingly I'm seeing lower hand raises when I say this. But if you've tried Microsoft Paint, if you remember, if you drew a line at an angle, it was very pixelated. It was basically a rasterization problem. And this is exactly the same problem here on the shape display. If you draw a line at an angle, you end up with a very uneven surface that is very unpleasant to trace with your finger. So we were trying to think of what is the equivalent of anti-aliasing on this physical hardware. And the method we thought of was, what if we instead render a horizontal line, and then we use the same illusion technique. So we're redirecting the user's finger in the opposite direction. So we're moving their virtual finger up, and they think that they have to go down in order to fix that kind of sensorimotor loop and get to where they need to be. So the result of this is that visually they're seeing a line at an angle, but on the physical display, they're actually following horizontal lines. And this makes it much easier to use as a rendering device. So here our goal was to figure out how far we could take this illusion before people noticed. So what we did was, we did this series of repetitions of different angles and different participants, repeated trials, and we asked people to tell us whether or not they thought there was an illusion. So they had to say yes or no to whether they thought we were applying an illusion or not, and we already showed them a very extreme case of illusion and an example of no illusions, so they knew exactly what we were talking about when we said an illusion. And we basically plotted the results from these repeated tasks. And here you can see on the x-axis we have the angles that we tried. We tried 5, 15, 25, 35, and I think 45. And on the y-axis we have the ratio of answers on average where participants detected the illusion. And this is a classic psychophysics task. And usually people will consider this point at 50% or 0.5 to be the point of where people are sort of guessing, 50-50, they're not really sure. And 75 is the point of detection threshold, where most people across most trials really notice the illusion. And as you see here, the detection threshold for this illusion was 50 degrees, meaning that we could do this illusion without people noticing up until 50 degrees, where they would really expect the forces in their muscles and ankle, wrist and elbow, and the forces in the joints to be very different than what it was. So if you're going like this in physical world, but you expect these forces, you start noticing the discrepancy. But this was actually much higher than we expected. I was expecting around 20 to 25 degrees, but we found that people didn't really notice these illusions till much higher angles. I will very briefly show another example of this, where we did a follow-up study actually below these detection thresholds, and we confirmed that people couldn't notice the illusion if we didn't tell them there was an illusion as well. And then we tried another example where we kind of scaled up the rendering. So here the problem, as you see here, the video. Okay. Here the problem you see is that there are only a few pins per area. So if you have a surface like a sphere, you only have a few pins, very rapid elevation change. Your finger gets caught in these gaps between the pins. And so what we can do instead is we blow up the rendering on the shape display and change the speed of your finger. And this allows us to basically make the display appear as if it was higher resolution, because now there are a lot more pins. And it allows us to render a lot more details on the shape display. So we did the same study to see how far we could take this, and we found that the detection threshold was almost 1.9 or 2 times the original size. So we could almost extend the size of the rendering, given the limitations of our shape display size, by 1.9 without people noticing that we were changing the speed of their finger. And we did the follow-up study, and we confirmed that people couldn't notice the illusion below 1.9, and that they generally preferred the scaled-up version. So I think the kind of takeaway from these is that our perception is very limited, and as long as we understand these thresholds, we can really mess with people's sense of proprioception and other things. And really, this is not the only, this is a very large research space. These were just 2 very specific examples of visio-haptic illusions between proprioception and vision. There are tons of other types of illusions across, yeah?
I kind of wonder, because I think this is very super cool, but if people live, spend a lot of time in virtual reality and they're subject to those illusions, does that something to them in real life? And as an example, I read an article yesterday about somebody who spent 10 years on cruise ships, and apparently he cannot really walk on land anymore.
No, that's a great question. So you're kind of getting at what I was hoping my students would do, which is longitudinal studies of perceptual illusions. But it turns out it's really hard to do longitudinal studies for a variety of reasons. But there are example literature in different, not within necessarily HCI, but in different kind of domains where people have looked at this. There's an example where prism adaptation, they basically flip your entire vision using glasses. And at first people are like, everything's upside down, and then they get used to it and they forget that it's upside down, they can function normally. And when you take off the glasses, it takes a while for them to go back, but what's more interesting is a sensorimotor task like throwing a ball. They can't perform that task if they've practiced in the other kind of domain, at least for a while. So that's a super interesting question of like longitudinal effects and what happens when you come out of these experiences. But these are, I would say, those are noticeable incongruencies, which I will get to. But these two examples are illusions. So people don't even notice that they're kind of experiencing these types of illusions, and they go away pretty quickly. Even if you're not paying visual attention, you're not going to be able to complete these tasks.
And even if people don't notice, do they still have some sort of eerie feeling? Because I think that when you're in VR, you have this, sometimes you have a feeling that something is off. You can't tell exactly what is off, but something's weird.
Yeah.
But would, you could imagine you have a scenario where everything is kind of twisted and everything's kind of, and the other one where everything is normal. Would people prefer, not that they know that it's twisted, but would they find the other scenario more natural or more smooth or something?
Yeah, that's a great question. So I think with these illusions, there's definitely this type of S-curve, where if you stay within the lower bounds of discrepancy, people really don't notice. Even as a researcher who worked on this every day for 3 years, I wouldn't notice. Then you get into this range of, first of all, there are huge individual differences. Like if you're a ballerina, you're going to have a very different experience than me sitting at my desk all day. And that range is when people have different experiences. In our studies, we tried to show people explicit examples of illusion, so they knew exactly what we were looking for, so that they would give us a more clear answer. But if you don't tell people that you're doing this, then you get this sort of adaptations that maybe people notice, but they don't really care. And that's what I'll get to in a bit, yeah.
Thank you.
Great. So I just wanted to give another example of some other people's research so that it doesn't sound like I kind of invented this field of perceptual illusions, because I certainly did not. I was just thinking about what are the practical use cases of these perceptual illusions for making interactions better, in this case, haptic interactions better. But there are other examples. For example, redirected walking is an example where people have figured out that we're really bad at knowing how far we rotate when we rotate our head. So as you wear a headset, if you rotate, you can actually change the speed of rotation of people's head during these rotational movements. And this is called redirected walking. And the very practical benefit is that if you're in VR and this is your room, you can make people explore a pretty large virtual space by just going back and forth in their room. And every time they turn around, you're actually manipulating the rotational angle during their movements. So this is another example of perceptual manipulations used to make VR experiences better, or appear as if they were better. So this brings me to my first question for the CITP community, which is, given how limited our perception is and how powerful, I guess powerful is a debatable word here, but how effective they can be, the perceptual manipulations, how can we make sure that people are safe as they interact? And not only the people in VR or augmented reality pass through headsets, but people around them. And this is one example of a paper that has done a workshop on kind of ideating some potential risks here. And this is something I thought about before reading this paper a lot during my research. I was thinking about what if I could redirect someone's hand towards a sharp object in their surrounding without them noticing. Or in these examples, they talk about redirecting someone towards a balcony instead of moving forward, or hitting objects or hitting other people without noticing as you're playing a virtual game. So these are some things that I think definitely worth thinking about and considering in terms of the severity of the risks and also the type of discomfort or safety concerns that may result from them. So now I'm going to kind of talk about maybe some of the things that Manuel and others were referring to, which is, sure, in these cases, we were what we were doing basically was that we were going from this one-to-one mapping between where people's real hand and virtual hand was into these illusory interactions where we made them slightly offset, or you could do other things. For example, you could make people's arms slightly longer and they wouldn't notice, and there's work on this as well. But you could take this further. You can actually have someone's hand totally different place in space where it's very obvious that's not where their hand is, but they can still adapt and learn how to use their hand in this form. Same with this famous kind of HCI example, the go-go interaction, where in VR, you don't have to be limited by the length of your arm. You can literally reach and touch really far objects, and there are studies on how long can the arm be before people lose control of this like sensorimotor task and things like that. So we call these interactions beyond real interactions, and really we were inspired by this paper that I think most people here would know, Beyond Being There, by Jim Holland and Scott Stornetta, which was published at CHI. And they, at the time, were arguing in the context of communication and collaboration. They were arguing why we need to think about computer-mediated communication beyond what we do in the physical space and really take advantage of what is possible with asynchronous communication and other things. And we were thinking along the same lines, like, why are we focused on these illusory interactions that keep this illusion of reality intact, and why can't we really take advantage of what is special about VR, which is you can have all these experiences that you couldn't have otherwise. So we started thinking about this notion of manipulations, not only in terms of people's body representation, but also manipulating space and time. And the key element, and the way I think of these beyond real interactions, are basically there's some sensory incongruency that you notice, but you don't really care because it's useful and you can adapt to it and you can take advantage of it in that way. So now I'm going to talk about two works in this space of kind of taking these mismatches further to a point where people notice that there's something going on, but they can still take advantage of them. So the first work is in this context of locomotion again, moving around in VR. And what we did in this work was we studied how people could kind of turn into giants and walk around at, let's say, 10 times faster speed, and then turn back into a one-to-one mapping. And this is a case where it's very obvious what's going on, but it doesn't matter because you can kind of learn and adapt to it. Another example here is the 7-league boots, which is a kind of well-known method for this type of speed gain, where every step that you take basically gets amplified. So instead of taking you one step further, it actually takes you 10 steps further. And this is an example of something that, as someone who's tried it all summer, I can tell you is very sickening, and we also did studies to confirm this. And what I'm trying to say by this is that there are sensory incongruencies that are acceptable, that we notice and we can learn and adapt to, and there are certain ones that we don't. And this is a clear example of vestibular visual mismatch, which makes people very sick. And so thinking about what are the right kind of sensory mismatches that we can take advantage of is kind of the point of these types of interactions. In the other work, it was more of a theoretical grounding, which I want to go through here. And basically what we were thinking about is how can we formulate these experiences that we are creating in AR or VR as how they integrate with people's physical or real world experiences. And by real world, we basically mean how people perceive the world and their surroundings through the sensory apparatus. And basically these beyond real interactions that I'm talking about, ultimately what they do is that there's a mismatch between the sensory signals from the real world and the virtual system. And at the end of the day, it doesn't matter if there's a mismatch there, because we're able to integrate those sensory signals and update our internal model to learn and adapt and really take advantage of the plasticity of the brain. So going back to what we had previously, I want to extend this diagram to how I think about VR and AR interactions. And I think it's a good framing in terms of thinking about what is different about AR and VR compared to the current form of 2D computing and the potential and potentially dangerous things that come from that. So let's go to the example of go-go interaction. I'm reaching and I want to extend someone's arm to be much larger. Basically what's happening here is that we need to do some form of tracking. We need to know where someone's arm is in space. You can do this with a controller they're holding in their hand. You can do this with the cameras on the headset. And then you need to transform that movement into some form of rendering. So in this case, the virtual arm, we are rendering it differently. So it could be virtual arm at a different place, or in this case, it could be a virtual arm that's much longer. So here, what's happening is that you're getting different sensory information from different systems. So when you increase someone's arm, basically what's happening here is that you're feeling the forces in your real arm. So this is proprioception coming through from the real world, from your mechanical body, and then you're visually seeing your virtual arm either being in a different place or in this case being much longer. So there's some sensory information that's being overridden by the VR or AR system. And so now you have this sort of mismatch that's possible with these wearable devices. And again, people can learn to integrate these and learn how to use them. I want to kind of talk about how so far we've been in the VR scene where you're wearing a virtual headset and we were re-rendering someone's avatar. And I want to show that these perceptual illusions are also possible as you move towards augmented reality with pass-through AR. And here I'll be kind of showing some of Mo's work, who's sitting right here. Mo is a postdoc in my group who recently joined 4 months ago, and we're very excited to have him. And I want to show some of Mo's previous work before he joined, because our current work is ongoing. Hopefully I can show that in a year or two. But Mo has worked on, pardon?
Or earlier.
2 years, 2 months to 2 years. So far, the stuff I've talked about have been in VR for body movement manipulation. And the examples I'm showing of Mo's past work is about perceptual manipulations of space and more towards augmented reality. So here's a work by Mo showing how you can basically delete someone and replace them by someone else, or in this case, a character, which is a less scary application. You can remove cars, which I'm sure we can all think about the risks of safety there. And this is 2021, which is in the rate of changes in this space is quite a bit long ago, and the types of techniques are much better now, and the output also much better. But you can maintain some aspects of the real space and alter it in some ways. Here's another work that Mo did at Meta when we were both there. He was working on this project. And I really like this project because it's kind of playful character, but gives you an idea of how much risk also comes with this type of thing, where you have this is a real space. This is augmented reality passed through AR. You have this character that's manipulating a physical object that is in space. So the tray is still there, but you think that the tray has been moved. And the character pushes the tray down the stairs, but the tray is still where it used to be. Or here, the elevator door is still closed, but it looks like it's open and you could run into it and you could hit that elevator door because you wouldn't know. And here, I guess one thing I want to, and also you can manipulate physical objects instantly in these examples as well. I want to do a quick plug that if this is interesting to you and you want to try it, we have a demo day in Princeton HCI coming up that you should come and try some of these examples. But here, these are also 2023, almost 2 years ago. Things have also improved a lot from then. And so things with Gaussian splatting and nerves, you're going to get reconstructions that really high quality. Even though this was really believable, and I've seen Mo demo it to many people in our lab, and every time people are reluctant to sit on a chair that didn't used to be there, even though it's been there all along. Even though this is very compelling, as we're getting better reconstruction and photorealistic rendering, they really do become indistinguishable. This is a capture that Cyrus sent me a few days ago of campus, and again, what's interesting here is that because our perception is limited, even if these reconstructions are not perfect, if we're not paying attention, we're going to believe what we're seeing as long as they're good enough. And so just wanted to highlight that things are moving fast in this space of, yeah.
One question I have here is that, is there a constraint on this adversarial process that's doing the manipulation? Because if what we are perceiving is through this headset device, potentially wondering like, why is it surprising that manipulations can happen? Is there, yeah, I'm wondering if there's a constraint in the manipulation process that
Yeah.
this adversarial system has.
Yeah, so I guess in some ways it's not surprising. So the first two examples I gave, the illusions are surprising in the sense that you don't even notice that they're there, right? And then you get into these spaces where you know it's not possible, for example, for a virtual character to move something, but at the end of the day, if you don't see the car coming, you're not gonna believe that the car is coming, right? It's I guess, is your question, how do we protect against these manipulations, or?
Yeah, just wanted to just understand the system model, the manipulations.
Mm-hmm.
So it seems like I'm perceiving the world through this AR system, and everything I'm seeing is being rendered through the system. So potentially the possibilities for manipulation are limitless.
Yes, so in theory, yes. But I guess in practice, it's actually quite hard to do this in real time, right? Because you have real-time camera feed coming through the headset of people moving, objects moving, your physical space. You're the one moving. And if you want to manipulate every single pixel, you can, and we're working on these examples, but you have to work on how do you remove an element and replace it with something else that's believable, that maybe follows the background of that object and the shadows and all that in the renderings. I don't know, maybe this is what you were asking, I'm not sure, but I guess this is a question I have, which is how do we prevent this? And I think from the group that is here, what's interesting to me, or maybe scary, is that when we think about social media and misinformation, I'm curious what everyone thinks about what this could look like, where we're all wearing headsets or glasses and we're literally living different realities, where maybe this misinformation is no longer our scrolling through our feed, but literally the physical space around us that we've subscribed to. And I think the scary part also is that the asymmetry, the kind of echo chambers, are also further amplified in this sense, because I can't see what any of the people around me are seeing, and how do you kind of balance that type of potential. Yes.
This is a very simple question. How does the Pokemon game fit into your picture?
Yeah, that's
there's some manipulation going on, and there was a lot of danger when people were actually playing the game.
Yeah, that's a great question. So I'll get into that in 2 slides, if that's okay. Yeah, so that, I think to your point, these are all kind of VR or pass-through AR, where you have this kind of chonky headset. That's the form factor is not very compelling. I think unless you're sitting down and experiencing one of these experiences that I started off my talk with, or doing some productivity application, you're probably not going to walk around the street wearing these. I hope. I assume people won't. And also there are other issues with VR. Even though it brings people together who may be not in the same physical space, it also kind of amplifies issues of social isolation. And there have been studies that, especially for people who are already socially isolated and low self-esteem, this has implications on their well-being. And so to answer your question, kind of moving towards the right, these risks change a little bit as you move towards the right, because you don't have as much control over how you intercept the sensory signals and the extent to which you can do that, because you're not kind of capturing the surrounding and re-rendering them, but people actually see through the glasses. But you still have all of the issues that you're referring to, which is safety, kind of information overload, and things like that. And that's why I think most of my group now is focused more on the right side of this chart, and we're thinking about what does the future of augmented reality look like with these see-through glasses. And we're thinking of also kind of going from low-level perceptual things to higher-level cognitive tasks, and thinking about how can we prevent the issues that we see with mobile devices in terms of information overload and over-reliance and distraction once we have a wearable that can show something at all times in the real world context. And this is a video that I really like, hyper reality, that kind of gives you a grim sense of what it could look like if you were wearing one of these glasses, and the level of distraction and safety issues. And there's a lot of incentives for this to happen in terms of marketing and things, but I think hopefully more of a thought experiment than what we will work towards. So I just want to end with a little bit of kind of high level of what my group is working on here at Princeton to tackle some of these issues. In the context of output, what we show, we've been thinking about how do we leverage different sensory modalities so that everything is not visual in front of your field of view that would block and distract you. So how can we leverage audio or haptic, and when is the right time to leverage those modalities? How can we keep the interface minimal so that you only see what you need when you need it and nothing more? And how do we show the person the right information at the right time? So Visa has been working on kind of thinking about timing of instructions so that they're not interrupting users and distracting them, and we only give information when there's some implicit cue that they need it. We've also been thinking about spatial computing as it interfaces with AI that's situated in our spaces, IoT devices and robots. How can we make use of AR as a way of explaining what's going on, allowing people to personalize these devices, make them predictable and also safe so that we can coexist in the same physical space. And Lauren and Mo have been working on these ideas as well. And then finally, we're thinking about what is the future of input, going from the mouse and the keyboard, how do we interact with these spatial computing systems the way we interact with people, or even more efficiently using our voice and gaze and gestures and other things. And Kyoso has been working on this space, thinking about how do we leverage different modalities, not just language, because so far a lot of these devices have focused on language only, and we're trying to think of how can we complement language with gestures and other things. And finally, one thing that we've been thinking about with Chingy is how do we make these consider privacy in all of this? And this is something I will pose more of an open question, and hopefully we'll have some projects to share. But this is an example, Aria glass that I set up a few weeks ago and I was using. And this is the type of data that you can see. You can see my pupils, because there's eye tracking on the glasses. So not only you can see what I'm looking at, you can see my pupil dilation, which is an indication of cognitive effort and cognitive load. You can see potentially some features that give you information about my emotional state and emotions. And you can also see the camera views looking out. So all of these are personally identifiable information. There's research showing that you can actually reconstruct the human body from these cameras, and the movement of the body. And there are many research showing that all of this is personally identifiable. Your posture, movements, and when I think about how much we get from just people scrolling and clicking on 2D interfaces to when we can know what they're looking at and how they react emotionally to this, scary. And so I hope that the question here we can all work on to make spatial computing privacy preserving. And I want to emphasize that this is a much larger magnitude than people think, because people think, oh, we already have all of these issues with 2D displays. What is different? And I really think this is the difference. It's the fact that we have this ability to intercept and read these signals at real time, reactions to environment at real time, and we can feed it back and get the feedback in real time. And so the magnitude and the pace is much, much higher than we previously seen. And so it's super important to start thinking about these now as opposed to when they're pervasive. So today I talked about these illusory interactions that leverage the limits of human perception towards these experiences that create incongruent sensory experiences between different sensory signals, yet people can learn to use them. And we discussed a few kind of questions around security, safety, the fact that we will experience different realities, and privacy. So with that, I want to thank my students working in my group and some collaborators. And with that, I'm happy to take any questions.
All right, we have 8 minutes for questions.
We talked about social media a little bit, but how is this going to move from 2D to 3D in terms of social interactions? Is that going to intensify the actual interaction? Because now you're kind of communicating using body language as well. And could there be a perceptual illusion that can be added to that interaction?
Yeah, that's a great question.
Accentuate those emotions.
Yeah, those are a great question. So that sub area, I would say, is not my area of expertise. I think about it as someone who's thinking in this space, but it's not something, social interactions is not something I personally research. But there's tons of research in this space, for example, from Jeremy Bailenson group at Stanford, thinking about communication and social interaction in VR. They've thought about the chameleon effect, where you can, again, it goes back to this feedback loop that I was showing, where if you can read people's facial signals and then in real time mimic them in a generated avatar or virtual avatar, there's research showing that people will like them better and trust them better. And so you can really take advantage of these kind of real-time feedback to manipulate people to buy things or believe things. And I do think it amplifies some of these issues.
I'm thinking if there are like discussions about the potential of advertisements in this, like this is also scary because it seems like a huge market to like be virtual reality and put like even more ads or like kind of like substitutes, I don't know, to like lower income interested people, users, like I don't know.
Yeah, those are a great question. I think that's what I was hinting at with the hyper reality and how it seems both difficult to believe but also very believable that there is incentives there for our attention to be taken away, for these manipulations to be used for purchasing things, and yeah, definitely. I think the bigger question is, how do we build the type of, in practice, how do we build the type of systems that me and my group and others are working towards with these minimal, just-in-time, calm devices? What is like the financial incentive for companies to do that versus not? Yeah. I don't have answers.
There's a meta patent on using your pupil reaction to promote advertising. So they've actually monetized, have plans to monetize exactly this.
Yeah, it's kind of clicking taken to the extreme.
Oh, On
at
that,
all
is
times.
there work suggesting that this is accurate? Like how accurate it is? Because I wonder. I could imagine it being accurate. I could imagine it also being slightly overblown. Like how accurately you can track emotions through pupil dilation.
So I think there are a few different things. One is gaze, like where you're looking.
Yeah.
That's very accurate.
Yeah,
We use it all the time in
yeah.
my group. Then you have pupil dilation, which has been shown to correlate with cognitive load. I'm with you on the whole facial emotion tracking, just because I think people are very different in how they emote. I don't think you have to go that far to do the things we're talking about. I think as long as you know if someone's paying attention, what's their intent, and what are they looking at, which are things that we're using as interaction techniques already, you could do this.
But you do have the heart rate, no? You could have the heart rate with one of the wristbands.
Yes, biometrics and like those things
and
are.
then you have like
Probably they have a heart rate thing here, no? Because it's probably possible to get like pulse from. It's crazy.
I know you posed this as a question, but with the like asymmetric realities thing, I was wondering how you thought about the different kinds of risks that come with asymmetries in VR versus AR. Like, do you see one as being more dangerous than the other, or are they just like very different kinds of dangers?
Yeah, that's a great question. I guess in some ways, VR, the interesting experiences are the ones that require a shared virtual space, right? Like the metaverse or these like social interactions where multiple people are interacting in a virtual space. The shared reality, I feel like, is incentivizing VR to some extent. Either you're by yourself experiencing something or you want to be with other people. I think it's, to me, the AR part, especially these like photorealistic manipulations are what is very difficult to entangle from reality.
Great. All right. Thanks, everyone. Thanks for us.
Thank you.